Welcome everyone to the algebra seminar. So today we have our own Ralf Schmidt, who's going to be talking about stable Klingen theory.
That's right, stable Klingen theory. Thank you. So in 2007, this book came out with my collaborator Brooks Roberts, and earlier this year another book came out with Brooks Roberts and Jennifer Johnson-Leung. So today I'd like to review what was in the old book and what's in the new book. So this is kind of a successor to the previous theory, so companion theory, I should say. So let me give some motivation. So let me start with an automorphic representation of GL2, 2x2 invertible matrices. So how should we think about this? I'm going to write it as pi being an infinite tensor product of local representations, but this tensor product really has no meaning. So you should just think about it as a collection of local representations over all prime numbers, and also the Archimedean prime, by which we mean the real numbers, basically. So these pi p's, these are representations. This means they have a vector space, and this is going to be a complex vector space. And this is a representation of the local groups GL2QP, where again, if P is infinity, this just means GL2R, and if P is a prime number, these are the p-adic numbers. And so an automorphic representation is a collection of such local representations with a sort of inner coherence property, which is pretty technical to describe, so I'm gonna just maybe leave that off, but think of it as just not a random collection, but it imposes a strong rigidity conditions on these local representations. So if we have such a collection of locals, then here's what we can do. We choose a vector from each vector space, some sort of distinguished vector, in the space Vp, which I said is a complex vector space, and they're all infinite dimensional. Okay? So it's sort of important to be able to somehow single out a distinguished vector in these infinite dimensional spaces. And this is basically what this whole talk is about, finding special elements in these big objects. So once we have that, we can piece them all together. And I'm going to write this as a infinite tensor again of all these local guys. And this is then, maybe we could call this a globally distinguished vector. And once we have such a thing, there is a process which is also a bit technical, but what you can do is you can sort of turn this into a function, f, on the complex upper half space. And this is going to be a holomorphic function with remarkable transformation properties. And this is what we call a modular form. A modular form, and the traditional name for the spaces of modular forms, they look like this. So an element of what's called sk, and then there is something called gamma 0 n. This number k here is a weight, called a weight. And it has to do with the infinity. So we chose distinguished vectors at every place, also at the Archimedean place. And depending on what vector you choose, you get a different weight here. And this n here has, this is a positive integer. And it has to do with the choice of our distinguished vectors at the pi p, where p is a finite drive. So let me not go into the details of how this stuff works, but let me
Could you say a few words? So are you saying that each component corresponds to modular form? And so the
component meaning
in your vector there?
so the whole collection here, right? So each globally distinguished distinguished vector will correspond to a modular form.
And the weight is only coming from the...
But the weight is only coming from the Archimedean place. And the level here, this number is called the level. The level is determined by your choices at the finite places. So it'll become more clear when I talk about how we actually make these choices at the finite places. So let me get into that. So here's how we sort of single out particularly nice vectors in these infinite dimensional vector spaces. We consider compact subgroups, and we call them k p to the n. So what is this? This is the group GL2 over the p-adic integers intersected with this set ZP, ZP, p to the n ZP, ZP. So it's 2 by 2 matrices, entries in ZP, but there's a congruence condition. You want the lower left entry to be divisible by p to the n. Okay. And the determinant is a unit in ZP cross. And you can check this is indeed a subgroup, obviously a compact subgroup because all these guys are compact, of GL2ZP. If n is 0, we mean all of GL2ZP. You see these groups, they become smaller and smaller, right? So kp to the 0 is the biggest one, that's all of GL2ZP. Then we have kp to the 1, and this contains kp to the kp squared, and so on. So now what we do is we look at this infinite dimensional vector space and we consider vectors that are fixed under these subgroups. So we consider, let me call it VPN. So this is the space VP, those guys that are fixed under kp to the n. Okay. And since these groups become smaller and smaller, these spaces become larger and larger. Okay, we're imposing less and less conditions. So it looks like this. VP0 is the first one, and that's contained in VP1, that's contained in VP2, and so on. And it may happen that the first ones are 0, right? You don't actually have any vectors that are fixed under kp0. Maybe the next one is also 0, it can go on for a while. And it's actually a non-trivial theorem that at some point you get to a place where you get non-zero vectors. So there is some place here, Vp, and a certain number which depends only on the representation, the local guy, pi p, where this space for the first time is non-zero. So you get maybe 0 dimension here, 0 dimension here, 0 dimension here, 0 dimension here, and then you get a non-zero dimension, and it's another theorem that says that the first time you get a non-zero dimension, you actually get dimension 1. And then the next one, you look at level np plus 1, you get dimension 2. And the next one will have dimension 3, and so on. So it's a very nice picture, and it looks like this. Lots of zeros potentially, but at some point it kicks in, and you get this nice linear growth. Okay. So not only that, but if you visualize sort of this vector, think of it as this dot. So this is this vector at level n pi p. Then there are two vectors here at level n pi p plus 1, and at level n pi p plus 2, we have 3 vectors, and then we have 4 vectors, and so on. And there is a very trivial operation, that's the identity map, because this vector is invariant under the group p to the n, the k p to the n p. So it's also invariant under the next guy, so the identity map provides a trivial level raising operator from one level to the next. Okay? So this is literally the identity matrix, 1, 1. But you can easily check that if you apply the matrix 1p, this is another level raising operator from one level to the next. Some simple algebra. And so these two always turn out to be linearly independent. So the next space is generated by the previous space using these two level raising operators. You can't keep going like this. So this is the identity. This is the other map. This is the identity. This is the other map. Right? And so you can generate one level from the next level. And obviously, if you go this way or this way, it's the same things, right? Because these two matrices commute. So we call all these vectors here old because they're generated by this guy, and this is the only one that's not old. So this guy here is called the local newform. This vector here. And so it spans this one-dimensional space.
Wait, what's the old?
All the other vectors are called old forms. Okay. So
All the ones below.
all the ones of higher level, they're called old forms. So this space here is generated by v new, so this is the new form. And this is going to be our distinguished vector in this representation. So this is how we find a special one in this otherwise infinite dimensional vector space.
Can you just say one more time, how do you get in this setting from the new to the old? What's the operation there?
This operation, these
Yeah.
operations,
Oh, it's just,
it's
like a hacker,
it's not really a Hecke operator, but technically it is. But it's really just applying this matrix, right? So
I see. Yeah.
so you have your new form, say, and you take the local representation and you literally apply this to it, and then you can check that the result is invariant under the next group, right? So.
Is this sort of chain of subspaces, is that a general phenomenon for sort of local representations, or are you using something about it coming from a global representation?
This is just local.
It's purely local.
Purely local, yes. It's nothing to do with global theory, really. Yeah. All right. So, if you're there with the classical theory of modular forms, there's something like old forms and new forms. There are these spaces. This is the level n, and what this level n is, it has a prime factorization, right? So write it as a product over primes p to the np. And what happens is that for each prime, we chose this local distinguished vector, and it has a certain level. This is this n pi p, and this will be the same as the exponent np here. Okay? If you choose the new form at every place. Okay? Now, maybe you make a different choice, right? So maybe you don't choose the distinguished vector, but you choose some of the old forms. Okay? Then you can still do the same thing. You can descend to a function on the upper half plane, and you get what's called the classical old form. Okay? So this space here will split up into a direct sum of the classical new forms and the classical old forms. And it's really the case that the classical new forms, they all originate from choosing the local new forms at every place.
So for all but finitely many p, this Vp0 is one-dimensional.
Indeed. So it turns out that for all but finitely many p, automatically the level starts at 0 here. Right? There are only a finite number of places where we actually have to go further, and that gives us the global level. All right. So we want to do something like this for another group, namely GSP4, and this is all what the first book is about. Okay.
Wait, it's p to the power n sub pi p.
Yes.
Okay, I just want to make sure.
That's right.
Just understand, okay.
That's right. So the NPs here are the
Same NP there.
N pi p's.
Okay.
That's right. Yeah. All right. So we want to do something like this for another group, namely GSP4. So what is this group? GSP4 now consists of 4x4 matrices, such that the condition is G transpose times JG is equal to some mu of G times J, where J is a symplectic matrix, meaning anti-symmetric. And I choose this J here. And the mu of G, this is a scalar here. So if the mu of G is 1, you get the symplectic group SP4. That's just the usual condition for a symplectic group then. And if the mu of G is allowed to be any scalar, you get a symplectic similitude group GSP4. All right?
Wait, say that again?
So if this mu of G is 1, then it's the classical definition of SP4.
You mean mu is the identity function?
Mu is literally 1, right? It's a scalar. So it's, I didn't specify the range.
Yeah, I mean, I don't mean the identity, I mean the trivial character.
Yeah, so those G where mu of G is 1, that's SP4. SP4 is the G in GSP4 where mu of G is 1. And mu of G is a homomorphism. It's called a multiplier homomorphism. All right. So we want to do something like this because if you do the same process, so instead of GL2, you take a collection of local representations of GSP4, then you end up with other objects here. I'm going to squeeze this in here. You would end up with, we call it big F, from H2 to C. So this is the Siegel upper half space of degree 2, which is a three-dimensional complex manifold. Okay? You again get a holomorphic function, and this is what we call a Siegel modular form. So just like classical modular forms originate from GL2, Siegel modular forms originate from GSP4, and if you would actually put GSP2n here, you would get Siegel modular forms of higher rank, but I'm only going to talk about rank 2 or degree 2 objects here.
Maybe you already said this, I missed this. So where's this holomorphic condition coming from?
The holomorphic condition, it's a good question. That comes from the Archimedean place. Okay. So it's like this basically. At the Archimedean place, you have a lowest weight 2, as a lowest weight k, and then you have k plus 2, and you have k plus 4. And then there's a gap here, and then you also have the weight minus k and minus k minus 2, and so on. This is how you visualize the Archimedean representation. And so each of these lines here corresponds to a vector in the representation, and this would be our V infinity, the distinguished vector at infinity, right?
Mm-hmm.
And since it's the lowest weight, that's what the holomorphy means. Okay. If
So
you
that's the way that to translate this to Cauchy-Riemann equation or something?
Yes, exactly. There is a level lowering operator, right?
Right.
And if you apply it to this guy, you end up being 0 because there's nothing here.
Right.
And that is really a differential operator on the Archimedean group, and when you descend, it turns precisely into the Cauchy-Riemann differential equation. It means holomorphic.
And this lowering operator, this is also, I mean, like, the way I think about this is the ordinary one for
Yeah.
SL2, so like
Yeah,
some power of y and then dz bar or something.
yeah, yeah, that's what it is.
I see. So I think the whole picture you're doing, you can also do for mass forms or something, right?
Yeah,
And so then this holomorphicity then would just translate into something else, like Laplace equation or something, or?
So for mass forms, you start with a different type of representation that doesn't have the gap. So you would choose maybe weight 0 in the middle. You can choose that. Right? And then there is no lowering. So you get no longer holomorphic objects, but you get some that satisfy some other kind of differential.
And this also comes from the Archimedean then? This,
Yeah, yeah.
But so where does it, so
It
there's
comes
no,
from the action of the center of the universal.
I see, from Casimir.
Casimir operator.
I see,
Exactly.
So this is like any setup.
Any setup.
You
so,
just have some lead theory and you have some centered universal enveloping algebra, and you don't really know what generates it, but whatever it's generating, you gotta find some generators.
Yeah. So you can do this in higher rank groups like GSP4. You know, then you have the Lie algebra. It acts on the Archimedean group. And if you choose an appropriate representation that's analogous to this, and some kind of lowest weight, then you end up with holomorphic Siegel modular forms. If you choose some other kind of representation that doesn't have a lowest weight, then you end up with some weaker Archimedean condition, some kind of differential equation that's satisfied. So the nature of the Archimedean representation here, the pi infinity, which I didn't talk about, that determines the nature of this modular form, whether it's holomorphic or mass or some kind of differential equation that it satisfies. Okay. So to do that same thing here, right, it would be nice to be able to also find distinguished vectors in local GSP4 representations. So how do we do that? And here, these groups kind of worked out nicely. Okay? And it's tempting to maybe try this again. So maybe in this case, try this. Try the set of all matrices in GSP4ZP intersected ZP, 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 P to the N CP. So these are now 2 by 2 blocks here. So this is the analog of this. Okay.
So this is all dependent on your choice of mu?
No, there's no choice, right? So mu is not a fixed character or anything. It's just saying all elements of GL4 that such that G transpose JG is a multiple of J.
And I see, and then it defines a homomorphism.
It defines homomorphism, that's right. Yeah. All right, so the choice of congruent subgroup is decisive. So this happens to work for this particular choice of subgroup. It's no guarantee, but it turns out it works. If you try the same thing here, it doesn't work. So what happens is that these spaces, you might get a similar picture, you get zeros in the beginning, but then you don't get 1 the first time it shows up. You might get 2. Or you might even get something, and John figured that out. It can happen that it depends on the prime, the first time you get something here, the minimal level, right? So it's kind of a mess. There's no way to define a good local newform using these groups, okay? So this is not a good theory. So then maybe we try something else. See, this is a parabolic subgroup here. It's the 2 parabolic modulo p. So what about taking the other parabolic? So you could take GSP for ZP intersected this set here. So this is the 1, 2, 1 parabolic. So what we're going to do is we put a p to the n here, p to the n, p to the n, p to the n, p to the n on everything below the blocks, and for the blocks we just put CPs everywhere. So this is called the Klingen parabolic, and so we call this the Klingen congruent subgroup. And that also doesn't work. Okay. So if you do the same thing, again, it's a mess. Maybe the picture like that, but at the minimal level you get who knows how many vectors. It's also the case that it may depend on P, right? So it's also not a good theory. But here's something that does work. So it turns out that this group here can sort of be enlarged to what's called a paramodular group. So what we do here is we have a similar congruence condition. So it's like p to the n, p to the n, p to the n, p to the n, p to the n. But then in this corner here, we put a p to the minus n. Okay. And the rest is CPs. So we allow a little bit of a denominator, okay, which is not something we've seen before, but it's still a perfectly fine compact subgroup here. And now we can try to measure the dimensions of the fixed vector, so we make the exact same definitions here. And it turns out we get a picture which is pretty much like this. In particular, at the minimal level, there's always one dimensionality. Okay? At the next level, there are 2 vectors. Okay? And at the next level, this number 3 will be 4. Okay? There are 4 vectors. Because there is now an additional level raising operator that raises the level by 2 steps. Okay? So we have a similar picture like this. And let me erase these matrices because they're no longer, now we're talking about 4 by 4 things, right? So it can't be like that. But there are 2 level raising operators from one to the next. And now there is this third one that raises the level by 2. Okay? So from here to here. And now it's no longer commutative. So to get to this spot, you can go this way or this way. And these are linearly dependent. So you actually get a sort of a multiplicity 2 here. Okay. And the same thing happens for every vector. So you get multiplicity 2, multiplicity 2.
So what are the weights there? Are they still scalars in this case then? Or?
The weights are still scalars at the Archimedean place. Well, I should say, if you choose your Archimedean representation appropriate, it's just a scalar. But if you choose it in a different way, you can get vector valued Siegel modular forms.
Then these are really different than the weights also, right?
Yeah, nothing to do with the weights.
Yeah.
Yeah. Yeah. All the weight stuff always comes from the Archimedean place only. Let me draw one more here.
So your circle is meaning
There are two
double
vectors. Yeah.
to dimension twice what you.
Right.
it looks
So
like.
so we get 1, 2, 3, 4. Right. That's this number 4. And the next number is 1, 2, 3, 4, 5, 6. Here. Right. And then we can keep going. Right. So this is this. So here this.
But there's never any overlap. It's a free process. Your generating function is like 1 minus t, 1 minus t, 1 minus t squared in the denominator.
Yeah, that's right. Yeah.
No interference.
No interference. Yeah. Right, so it looks like this. And this is, in fact, the cover picture for the first book. Okay. So this is the story, and in particular, it's still possible to find a unique local newform here. Right, so this gives us a global theory of all the new Siegel modular forms, and it works just as well as this one. Okay. So this is the theory of paramodular